Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today we are continuing with differentiation, looking at a somewhat unrelated but very important topic, polar coordinates. So if you're ready to learn, then let's get into it. Now let's discuss polar coordinates. So this is basically a different way of thinking about our coordinate system. So you'll be used to x and y as are just linear, x being like left and right and y being up and down. And obviously you can have z to be in and out of the page for a 3D, but for just polar coordinates to start with, we'll be looking at 2 dimensions, and I'll explain in a later course how this could be extended to different versions of polar coordinates. So there's the main 2 that are used throughout physics are spherical polar coordinates and cylindrical polar coordinates, both of which are very useful in different cases. So our foundation is just going to be our 2-dimensional polar coordinates. So instead of x and y, our coordinates are going to have r and theta. And here, r is the radial distance to the origin, and theta is the angle, and it's defined as this with respect to the positive x-axis. So if I just draw our Cartesian coordinates to start with, we have x, we have y, and let's say there's a point on our graph P. We could redefine the sort of values given for this point in our polar coordinates, and this will be our radial distance here, so r, and this angle here is our theta. So that's a visual representation of what I just said above, and these are actually always equal, their definitions. So the way we can convert between Cartesian and 2D polar coordinates will be r, you might be able to, well, you should be able to work out both of them, but r is x squared plus y squared square rooted. And you could just imagine that if this distance here was 3 and this distance here was 4, we have a 3, 4, 5 triangle, and r is going to equal 5. That's the actual distance to the origin. And then theta is just going to be, imagine again, actually it was 3 and 4, but if you imagine this distance here is the 4, this is the 3, you can see that we're going to be using SOHCAHTOA, or tan is opposite over adjacent, so you're going to have arctan of y over x, whatever our y and x values are. And these theta values are going to go from 0, where it's pointing along the x-axis, up to 2 pi. And obviously when it is 2 pi, that's going to be also the same as 0, it's going to be pointing along the x-axis. So you can see it will just sort of traverse round in a circle. And then radius, I should have said, is obviously going to always be greater than or equal to 0. Because if you thought maybe, I don't know, a negative radius here will point down here, that's the same as whatever angle this is, plus pi, and then it's just, again, a positive radius going outwards. So I'll leave it to you as an exercise to show how, if we know our r value and our theta value, how we could convert back to our Cartesian coordinates by these 2 equations. So x is equal to r cos theta, and y is equal to r sine theta. And just check for yourself why that is the case. Look at the graph, draw some lines on it, draw some triangles, and try and work out why we know that's true. So an interesting example of where polar coordinates in 2D come much more into value than Cartesian coordinates is with the Lemniscate function, or also known as the figure of 8 function. And this is where r squared equals 2a squared times cos of 2 theta. And you could look at this as familiar in a sense if you said it was like a y squared equaling some function of x. And that's just, I mean, you could square root it and it'll still be y equals a function of x, right? So we've just got this different coordinate system. What we can do straight away is, as we are defining r to be a real number and it's non-negative, it must mean that cos of 2 theta has to be above 0, because if it was less than 0, we'd have r squared trying to be a negative number, and that just doesn't make any sense. We're also assuming here that a is also a real number. So if we had cos of 2 theta less than 0, it would lead to r squared less than 0, which makes no sense in our case. And this cos of 2 theta being less than 0 is the same as our 2 theta being less than pi over 2. I mean, greater than pi over 2 and less than 3 pi over 2. Or our theta being between 3 pi over 4 and pi over 4. We don't want that range, so outside of that range is fine. And if we did pi plus these values, we'll still be less than 2 pi. So for this top one, it will be 7 pi over 4 and 5 pi over 4 on the bottom. And we are again saying between these two values, it cannot be the case that we have a drawing of our graph above, because r squared would have to be a negative number, and that would mean we've got complications there because r we've defined as real. And so if we draw this, we'll say this dotted line here and this dotted line here can show our sort of asymptotes, in a sense, that up this way is theta equals pi over 4, down here is theta equals 7 pi over 4, up here is theta equals 3 pi over 4, and down here equals 5 pi over 4. And we were saying between these ranges, so between pi over 4 and 3 pi over 4, we can't use this region. And similarly, we can't use this region. And so what we're left with is drawing some function in the ranges that haven't been shaded in. Actually, if we look at what could be the maximum x value, but here it's going to be our maximum r value, and that will be when cos is 1. So r squared equals 2a squared, or r equals the square root of 2 times by a, and down here will be minus square root of 2 times by a. And that will happen when theta is 0 or pi, so that will be along our x-axis in a sense. And so to draw this, we're going to be ending up with this sort of shape. As you can see, that was very badly done, but it's basically meant to represent this symmetric figure of 8. And then our final example will be an ellipse again. And I'll leave it up to you to look into this if you're interested. It's probably beyond the scope of this sort of module, but it will be defined as L over R equals 1 plus E cos theta. And I want you to think about, why does that result in an ellipse? How does it look, and how is the eccentricity related to all these other values? And by comparing it to before and seeing our Cartesian version, how they sort of compare. And just a small side note, for our eccentricities, as I said before, E equaling 0 leads to a circle, but E equaling 1 leads to a parabola, and E is greater than 1 leads to a hyperbola. And anything between 0 and 1 is our nice ellipse. This is just very interesting for planetary orbits, and as I specialise in astrophysics, this is sort of the bread and butter for some parts of astrophysics. So if you're interested, look into it, but I won't waste time by just going on about it in this video. Today we've covered the basics of polar coordinates. In the next video, we'll be looking at the polynomial and series representation of curves. So if you want to learn more, I'll see you in the next one. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.